So in the spirit of this class, and the idea that this class is about ideas and concepts and connections rather than just procedures and memorization, let's think about everything that we've done, essentially, okay? So what I've got here are two graphs. On the left, I've got a rate of change graph, and on the right, I have an accumulation graph, okay? So if you want to think context, let's make the left like the rate of change in elevation of a highway as you drive towards the coastline, or maybe away from the coastline. Okay, so this will be like, feet per mile of elevation as you drive away from the coastline, so miles down here. And so then if I'm accumulating, so if that's my rate of change, then what should I label my axes in my accumulation function? So the horizontal axis is going to be still in miles, because you accumulate elevation as you drive away from the coastline. And what's going to be over here? Feet, right? Excellent. Okay, so what I would like you to do is tell me two ways that I can describe the change in elevation between 2 miles and 7 miles. Okay, so I want two different expressions that will describe the change in elevation between 2 miles and 7 miles. So take a, Can I make the graphs bigger? Oh, you don't need numbers to answer this question. So I'm asking for two expressions. How would you represent the change in elevation between 2 miles and 7 miles in two different ways? So I'm not asking for the exact, I'm not asking for an estimated value right now. I don't need numbers. I want expressions. Okay, how could we do this? Does this help? Do you need to talk to each other? Yeah? Oh, you're giving me answers already. I don't think everybody's thought totally yet. I want you guys, seriously, think about it, right? Because we know how to do this. We did this. It's been a while, but the ideas have been there, right? So think about it, right? So you have a rate of change function, and you have an accumulation function. And so right now, I want you to concentrate on this approximate rate of change function to answer my question, okay? So there's one big hint, right? One of the ways that you're going to create an expression is using the rate of change function, okay? The other way is going to be using the accumulation function, okay? All right. So I had some good conversations with you guys, so let's bring it all together. So I saw a lot of you opt to call the accumulation function over here y equals f of x. And so if you wanted to represent, so we're going to do this step by step, right? So if I wanted to represent the amount of accumulated elevation at 2 miles, how would I represent that? The accumulated elevation at 2 miles. F of 2, right? So at 2 miles, F of 2 is, so that's this, somewhere around here. So F of 2, that's the accumulated elevation at 2 miles. So for at 7 miles, it's somewhere, somewhere over here. So right here, abouts, would be F of 7. That's the accumulated elevation once you've traveled 7 miles from the coastline. So then the change in elevation would be F of 7 minus F of 2, right? That difference between these two, so this distance here is the change in elevation, okay? So that's one way to represent the change in elevation, okay? What's the other way? So looking at the left-hand graph, Roche? Okay, so you recognize that from 6 to 7 is 1, that's half of our delta x. It's okay, we'll just write 1. Okay, that's that change in x, right? Okay, and so, so let's sort of compare what we've got here. So notice that this is, this is an approximate accumulation, right, from 2 to 7 miles, where each of these terms, so remember you get, so this multiplication, this rate of change times the change in x gives you a little bit of accumulation, right? We worked really hard at the beginning of the semester to talk about this relationship, right? And so that's coming back. That's what we're using here, okay? So, so I've got that approximate accumulation here. Is this exact or approximate? So this accumulation function over here, is it exact or approximate? This is still approximate, right? This is the accumulation function that I built using the step rate of change function on the left, okay? So what's going to happen if I change my delta x to be smaller? Everything will get more and more accurate, right? So I change my delta x to get smaller and smaller and smaller, right? And things get smoother and smoother, right? And prettier, okay? And more accurate, okay? And so actually if I, so here's my approximate rate of change function, right? My step function. If I turn off my exact rate, you can see how good our approximate rates are because we let delta x get so small, okay? So so now if I ask you the same question, right? So let's turn this bad boy back on, okay? So it'll be darker. So now I essentially have my exact accumulation, right? And basically my exact rate of change. So instead of calling this f, let me go ahead and change its name because it's no longer an approximation. So we'll call it a of x. We'll still call, what do you want to call this? R sub a? How about that? Okay. So how could I, so now that delta x is so small, I certainly wouldn't want to add up like, r sub 100 delta x plus r sub 101 delta x all the way up to like r sub 10,000 delta x, right? Like I just don't want to do that. So what did we do to avoid having to go through and write down a summation of 10,000 terms? What did we develop? the integral, right? So the way to represent the change in elevation using this left-hand graph, how would I write it? You guys just told me I'm going to add up from 2 to 7 little bits of accumulation. How do I get little bits of accumulation? The rate times little changes in x. Okay? So this we called the open form, right? Because it shows you the process. So when I look at this expression, and hopefully when you look at this expression, you see what I just said out loud, right? So we're adding up, so this like German S for summation, from 2 to 7, the rates times a little bit of change in x to give, so these are representing little bits of change in accumulation, okay? And we're adding them all up, okay? Now on the right, how do I represent the change in elevation? I heard this. Right? That part doesn't change except for the fact that now we have the exact accumulation function to work with, right? But it's still, the outputs of this graph are still the accumulation, only now they're exact accumulation rather than approximate accumulation. So if I want to find the change in accumulation using the right-hand graph, I can still literally find the change, right? The difference in accumulation, okay? So this would be closed form, right? But they're both exact. So they're equal, right? Both of these are representing the same quantity. Both of these expressions represent the change in elevation as you move from 2 miles to 7 miles away from the coastline, okay? So that's for specific numbers. If I wanted to talk about functions rather than exact values, right? So rather than being fixed from 2 to 7 miles, if I wanted to, like start at the coastline and keep track of my change in elevation, where would I start if I'm starting at the coastline? Start at 0. And then I want to be able to keep track of my elevation at any distance. So I'm going to call that x. So then what should I put inside of my integral? R sub a of, I think we've been using t's, dt, right? But the thing is, it has to be something other than x, right? Because this x now is telling us where our sort of stopping point is, somewhere, right? And so we need something else to keep track of the changing quantity as we go through, okay? So then if I wanted to write it in closed form using the accumulation function, then how would that look? A of x minus a of 0. Right? Okay. And if I didn't want to start at 0 and I wanted to start somewhere else at some a value, then I'd change it like that, right? And so the difference between this expression here and the expression I have up here is that in the lowercase, those are actually representing numerical values, right? Like if I actually gave you a rule, which is right here, right, you could actually go through and compute those values. Whereas this upper equation that I have, those are like this on the left side is what kind of thing? Is it a value? No, right? If it's got an x up here, right? This is a function, right? as is this stuff on the right, right? Because a of x, that's a function. And I'm just subtracting a constant from it, so it's a function still, okay? So this is giving us a function to keep track of change in elevation, whereas this is like as if I had already plugged in some numbers and evaluated the function somewhere to get some numerical output, okay? So, all right. So let's look at this sort of all put together, okay? So what we just did was sort of a rehash of this whole process of getting accumulation from a rate of change function, okay? And so if we have a rate of change function, then we just established that the accumulation function defined by R beginning at A can be expressed in this fashion, okay? So what happens if I wanted to find the accumulation not starting at A, but starting at some other value C? Right? That's a reasonable question to ask. Can you guys think of what you might do? So I want to now figure out what the accumulation would be. Instead of starting at A, I want to start at C. But I have to use what I'm given. So imagine that you're talking about having accumulation. So you've got some starting place, A, there's some C value here, and ultimately you're ending at some X value, right? And so my function f gives me accumulation from A to X, but I only want the accumulation from C to X. Well, okay, without doing that. Subtract what? Okay, so if I have accumulation from A to X, and I subtract accumulation from A to C, that'll give me the accumulation from C to X, right? So you jumped straight ahead. So what you just said is here. So the accumulation from C to X is the accumulation from A to X minus the accumulation from A to C, okay? Does everybody see what's going on here? Okay. But notice that the accumulation from A to X, we called that F, right? What about this? The accumulation from A to C. How could I, so this right here is F of X. What would this be in terms of F? I heard somebody say it. F of C, right? Because you've plugged in C for X. Okay? So we have this relationship. So this is, so in case you were wondering, this is a big deal, okay? We have just established a relationship between our rate of change function, right, and our accumulation functions. Oh, wait, we've been doing that all semester. But this is a big deal, okay? This is called the fundamental theorem of calculus. So anyways, okay, just a small thing. That's what's so cool about this class. We've been doing that all along. Okay, so what does this do for us? Okay, so this is the big deal relationship that everybody strives for in calculus. Okay, we're just cool enough that we've been talking about it all semester. But let's think about this a little bit. Okay, so if I start with an accumulation function, f of x equals x squared, what is its rate of change function? 2x. Okay. So I can now relate those two equations. Apparently I decided we're starting to talk about accumulation at 3. Okay. So I can talk about the accumulation of f from 3 to x using this open form integral notation that incorporates the information about the rate of change, and I can relate that to the actual accumulation function. Okay? Now, this probably seems way uncool at the moment because I handed you the accumulation function, and then we found the rate of change, and then just said, oh, wait, look, there's this relationship between them. Okay? But remember, part of the thing that we've been doing is, okay, so if I give you the accumulation, you can find the rate of change. Okay? But we haven't totally addressed the reverse situation in an easy way, right? So we've done that using the mastery test and learning all of these derivative rules and figuring out how to do that quickly to go from accumulation to rate of change. But what if I want to go backwards? Okay, what if I give you the rate of change and I want to find the accumulation? Okay, that's what this is giving us. Okay, so if I hadn't given you this to start with, okay, this relationship is going to be where it comes from. Okay, where we get the accumulation from. Okay, so that's what we're looking at here, right? So if I give you the rate of change, then you can come up with the accumulation sort of by doing the reverse process of what we've been doing with the mastery rules. Okay. So once again, just to sort of like get in the flow of this, right? So I'm going to give you the accumulation function for a second. What is its rate of change function? So the derivative of e to the stuff is e to the stuff times the derivative of the stuff, right? So e to the x cubed times 3x squared, okay? So now pretend for a second that I didn't tell you that, okay? And I only gave you the rate of change function. And I say, I want the accumulation function, okay? Then you would use this relationship, right, to say, okay, well, I've got the rate of change. Let's say we're accumulating from -2. Then I know that this is going to equal, using this top relationship, the change in accumulation from, x to -2, or -2 to x. Okay? We're going to not do that for the sake of time at the moment. Okay? Well, no, we should. Okay, so no, we're not. Okay, sorry. I want to make sure that we get through some of the cool stuff. And then we'll go back if we have time. So, okay. So this is the full circle, right? So at the very beginning of the semester, if we had a rate of change function in closed form, then we were able to get an exact accumulation function through that whole process of creating the approximate step rate of change, to get the piecewise linear approximate accumulation, and then let delta x get really small to give us the exact accumulation, right? So that was the first step in our journey, okay? And we ended up building up this right, this integral notation to talk about that, okay? Then we sort of switched gears, and we looked at the reverse problem, where I give you an exact accumulation function in closed form, and you find the exact rate of change function in closed form, right? And so the sort of the process that we went through to do that was to talk about average rate of change, right? So given your accumulation function, we found the average rate of change over intervals, and then that gave us a step rate of change function, and then we let the size of the intervals get small, and that made the step rate of change function get really close to the exact rate of change function, right? So it's sort of this reverse process. And then we said, hey, if we think about that and sort of formalize that, we were able to use that sort of the definition of the derivative, right, which takes this expression f of x plus h minus f of x all over h, which is an expression representing the average rate of change over an h interval, right? and makes that get small. That's what that does, right? So we took that definition to then create our quick and easy rules for finding derivatives, right? But don't forget about that process. We went through that, like rules, the definition of the derivative process. You should study that for tomorrow, right? To get to our mastery rules, okay? All right, so that gave us the reverse. Okay, well, these two things are exactly the same, right? And so our mastery rules told us how to go from exact accumulation to rate of change. But now we want to go from rate of change to exact accumulation, okay? And that's what we're doing here, okay? So we're completing the cycle, going full circle, okay? So some more examples. So what is this thing going to equal? F of x minus f of 1. Since I already know what f of x is, because this is just an example to make life easy, what is that going to look like? E to the 6x to the 4th minus e to the 6th, right? Okay. And then we've got some more. So let me, again, I want to make sure that we get to the punchline. So this is important. Sorry, I had a lot of examples ready for you. Okay, so suppose that f and g are functions, okay? If g is the derivative of f, i.e. g is f's rate of change function, then f is called an antiderivative of g, okay? So thinking in reverse. So g is the derivative of f, means f is the antiderivative of g, okay? So f, derivative of f, go in reverse, you get the antiderivative, right? Okay, oops, I said the wrong word. I said the antiderivative. In fact, that's not appropriate, okay? So it's an antiderivative, okay? So why do I say that? So every accumulation function is an antiderivative of its rate of change function. So the implication here is that there is more than one antiderivative for a given rate of change, okay? However, every rate of change function has more than one antiderivative. So we've seen that, right? So when I've given you a rate of change function and we've talked about sketching the corresponding accumulation function, I've always had to give you a point to ground yourself in, right? I have to say, oh, okay, well, suppose that the accumulation is 5 when x is 0. Now you can start trying to draw your graph. But until I give you that point, you don't know where to place your graph. And it could have been anywhere. It could have been higher, lower, you know. So let's see how this works and how this comes out of what I've introduced today. So every rate of change function has more than one antiderivative. So here's a rate of change function, okay? From this relationship, what can I say? So that is equal to what? Can you see it? So this is the integral from 1 to x of 4t cubed dt. So this is equal to sum f of x minus f of 1, where f is the corresponding accumulation function, right? Oops, let me write that down. So f of x minus f of 1. What about here? F of x minus f of negative 5. What about here? Okay. So in particular, if I were to solve for f of x, right? It could be this, or it could be like this thing, right? And the fact that I'm adding different numbers over here, that's giving me different functions, right? So really, I shouldn't call both of these f, because these are actually different functions. Question? Oh, I solved for f of x. So I added f of 1 to this side, and then I just swapped the order in which I wrote them. Can we make my life easier for a second? Can you think of think of a function that would have this as its rate of change? X to the 4th, right? So here's one such function, right? Here's a couple of other ones, right? And we could keep going. Okay, so the improper integral, so actually let me piece this together. So we've said that this is one function whose rate of change will give me this. So if I were to rewrite these things, this would say x to the 4th minus pi to the 4th, right? So this is an example of an accumulation function whose rate of change is 4x cubed, right? Because if I take the derivative of this, the derivative of pi to the 4th is 0. So I just get 4x cubed, okay? Whereas up here, it would have been x to the 4th minus negative 5 to the 4th. And up here, it would have been x to the 4th minus 1. So those are three different antiderivatives for this rate of change function, okay? So if I want to sort of collectively represent all of the possibilities, okay, that happens when I don't put bounds on my integral. So notice that there's no lower limit and no upper limit on this integral notation, okay? So this is what's called an improper integral, and it's used to represent all possible antiderivatives. So what do I mean by that? I actually don't like this. I meant to delete this. Ignore this. I mean that we include some unknown constant at the end, right? So there's some unknown constant. Well, it's not that this is unknown. It's that this represents all possible constants collectively, okay? So C could be anything, okay? And this would be a way to represent all possible antiderivatives in one fell swoop, okay? So then give me an antiderivative of g of x equals x. So when you're trying to think of an answer, you should be asking yourself, what has a derivative of x? So I'm hearing a couple of different things. So I'm hearing x squared. What's the derivative of x squared? That's 2x. So how do I account for the 2? I divide by 2, right? So x squared over 2 is an antiderivative of g of x equals x because the derivative of x squared is 2. Whoops, that wasn't supposed to happen. Okay, here's another one, right? X squared over 2 plus 1 because the derivative of that is also x. And so on and so forth, okay? So that's why we use this last plus c to represent generically what an antiderivative of x would look like, okay? So when you're doing your homework for Friday, this is how you should think about it, right? If I ask you to find an antiderivative, the question you should be asking yourself is, what accumulation function has the given thing as its rate of change? Okay? So you don't have to learn new rules because you've already memorized them in one direction. Okay? So now you just sort of have to train your brain to think in reverse. Question? Yes, test 3 is tomorrow. I have office hours today after class. Mark has office hours tomorrow. And so your homework was split up so that you have an assignment due tomorrow based on the material from Monday's lecture, because that material is not on the test, nor is today's material. So I wanted you guys to have a little bit of extra time to like take the test and then go and work on that homework if you wanted to. Okay?
What time is the